welcome back. So we were talking about this idea of like setting targets for climate change and so on, and how, there's going to be some temperature that the climate system will reach that's a function of the amount of carbon dioxide we ever emitted between the Industrial Revolution and the day that we figure out not to do that anymore. And notice that this kind of, it's an interesting intellectual puzzle here, because there's three issues hidden in here. Three key concepts in the field of climate science are irreversibility, commitment, and stabilization. And these words might mean slightly different than what you think they mean, at least in a physical climatology context. So let's pick these things apart here in this part of this lecture here. Irreversibility. This is a concept that comes to us from climate science, and it's defined in the IPCC report and in various textbooks and so on. The IPCC report defines, well, let me use their jargon here. They define a perturbed state, that is something, a climate system that we have changed by doing things like changing the radiative forces. The IPCC report defines a perturbed state as being irreversible on a given time scale anyway. All climate could eventually change, but on a given time scale, like thousands of years or whatever, if the recovery time scale from this state, due to the natural processes, is significantly longer than the time it takes for the system to reach the perturbed state. That's really full of jargon. Let me use the best example here. Climate change due to carbon dioxide being added to the atmosphere. We can add carbon dioxide to the atmosphere as fast as we want. And the climate will change based on how much carbon dioxide we have added. It won't happen immediately, right? We've learned about the thermal inertia of the climate system and so on. But on the order of decades, the climate system will change based on how we have perturbed it. Natural processes will return it back to its pre-industrial climate. The carbon cycle will gradually remove that carbon center. But that takes orders of magnitude more time than it took to get to that perturbed state, right? We only needed a few decades to adjust and reach that warmer climate. It's going to take millennia to recover. That makes that, by the definition that we use in climate science, that's an irreversible climate change. It takes much longer to get back from that state than it took to get to that state. And in fact, lots of different climate changes are irreversible. We talk about melting permafrost as an irreversible climate change. Okay, it takes a relatively small period of time, a few years of warmer than normal summers, to start melting permafrost, and then you get the problem of it decomposing the materials that are in it and so on. Building that permafrost back up takes vastly longer. Okay, hundreds of years or something like that. It's an irreversible climate change. All right, irreversibility. Well, if you actually take a look at like some of the model runs for different RCP, remember the pathways, you could see the top panel here is showing the actual amounts of the radiative forcing associated. Well, actually, they've converted it there to parts per million by volume for carbon dioxide. But you remember we had all these different scenarios out, in this case, to the year 2300. And you look at the temperature changes that we see in the ensembles of models there, and even in the best scenarios, like RCP 2.6, where we have the smallest radiative forcing, a really unrealistically small radiative forcing, the temperature does not return to pre-industrial levels, even on the term scales of hundreds of years. And we're not going to have a 2.6 watt per square meter radiative forcing. It's going to be more in the range of 4 to 8 watt per square meter. And you start looking at those curves and you see, wow, the temperature barely even starts going back down to pre-industrial levels on those time scales. That's a problem. That's irreversible climate change right there. And actually, some of the model runs extended much farther. Like if you look at the x-axis of this diagram here, you can see that these simulations go all the way out to the year 3000. Now, these are not full numerical models. This is done a different way. It's not terribly important for where we're going here. But the point is, if you could actually extend the zero line from the y-axis across there, you can see that really, even on the time scale of like another 1,000 years, well, maybe that unrealistically small radiative forcing gets kind of back to pre-industrial levels, but the other one's not even close. They're not even really trending down yet. Thousands of years into the future, we're still dealing with climate change caused by the relatively quick addition of carbon dioxide to the atmosphere in the 1800s, 1900s, early 2000s, etc. Oh no. That's what we mean by irreversibility in climate change. We also talk about commitment. Now, commitment isn't as in like, oh, we're committed to doing something different. No, this is climate change commitment, and it has to do with the fact that the climate continues to change further after the forcing or the emissions have been eliminated or held constant. We actually talked about like committed warming in earlier modules of the course, where we talked about the fact that, like, you know, the Earth is not yet in radiative balance based on the greenhouse gases we have already added. Even if we stopped adding greenhouse gases to the Earth's atmosphere, because there is a net warming of the surface of the Earth, every day the planet would be warmer than it was the previous day. Until we reach a new radiative balance, we are committed to a certain amount of warming just based on the stuff we have already added. So, just to be clear as to how this is going to work. There's actually kind of a technical jargony definition of commitment and so on, but the idea is that we're going to talk about how, like, if we just, in a model simulation, said, as of 2017 in our model, we're going to assume let's run a model simulation where we doubled the amount of carbon dioxide in the Earth's atmosphere. And we just add it as a step change. In 2016 in the model, we had 400 parts per million. 2017, let's have 800 parts per million. Well, for a little step change in the forcings like that, a large portion of that total radiative forcing will be used to create a climate change at this like surface temperature pretty quick. Within a few years, a big chunk of the total change will have happened. But the remaining response would happen over a long period of time. It would take a long time for the system to reach its final radiative balance. That's part of the reason why we still aren't at a radiative balance based on past greenhouse gas emissions. You know, that's why the climate system, like we learned about in the first module, is not in radiative balance, or the second module is not yet in radiative balance. The remaining response is going to take on the order of centuries or whatever, and that is called the climate change commitment. And it's a complicated thing to figure out because the response time scale is very complicated. It depends on things like how much of the carbon it stays in the atmosphere versus gets moved to other parts of the carbon cycle, especially into the ocean and so on. In fact, that's a big problem because there are very different time scales as to how fast we move carbon in and out of the different parts of the carbon cycle. And we move carbon in and out of the land biosphere at a very different rate than we do out of the deep ocean, and at a very different rate than we do out of, say, the lithosphere. This is all very complicated to actually figure out where that commitment is going to end up in terms of it. But this kind of stuff is just made for climate models. This is the kind of stuff numerical models of the atmosphere are going to be great for testing, because all we got to do is run it using different assumptions. That's what science does, right? Well, it turns out you could take a look at these kinds of studies where teams of researchers have run climate models trying to figure out what is the commitment. What are we going to end up with here? For example, constant composition commitment studies are a whole class of studies that climate scientists will do. Well, they will run models where we determine the amount of warming that will happen after all of the constituents of the atmosphere reach a particular level. Like, let's say we're going to run the model with constant amounts of carbon dioxide at 800 parts per million. Okay? Or the value of the amount of carbon dioxide that was observed to be in the atmosphere in the year 2000. And we're just going to run the model out, not changing those boundary conditions, and just find out where will the climate stabilize? Where does the amount of committed warming? Oh, we reach by the year 2100. Like, I actually highlighted a result there. If you run the models using the amount of carbon dioxide that's in the atmosphere as of the year 2000, you run it out, and by about the year 2100, you can see that we have about 0.6 of a degree more warming. Okay, completely unrealistic. I mean, frankly, that involves a time machine, right? We would actually have to go back to the year 2000 and get rid of all the carbon dioxide that we've added to the atmosphere since the year 2000. But the idea is we're trying to get a sense here. How big are these changes? Where does our climate end up? There's another whole set of scenarios called constant emission studies that determine the amount of warming that would result from maintaining our current anthropogenic emissions at some level, like maybe the current level or some specific level. And in many ways, this is kind of the more realistic scenario, because it's hard to imagine that we're going to be able to get completely off of fossil fuels anytime in the near future. Realistically, our best hope is to stop increasing the rate at which we are adding fossil carbon dioxide to the Earth's atmosphere. So a lot of studies do this. In fact, one of the earlier diagrams we saw, the one that had the spike in the temperature, if we just stopped emitting altogether, you might have noticed that the red curves there were for constant emission commitment studies, where they were saying, let's just hold the emissions. Let's say we could at least stop increasing our emissions. All right, we're still burning fossil fuels, but at least we're not increasing the amount we burn each year. That's a great idea. At least we need to know what those mean. And like, for example, if we said, let's just say starting in the year 2010, we're not going to increase our emissions anymore. We can still burn at 2010 levels, which is a horrifying amount of fossil fuels. Well, we end up with 1 to 2.5 degrees of temperature increase between now and the end of the 21st century, which the important result here is notice how much more that is if we had just stopped. Okay? The climate change commitment associated, the committed warming associated with these constant emission scenarios is greater than the amount of committed warming that we are seeing in these scenarios that involved stopping emitting, which of course makes perfectly good sense, but now we have a sense of the magnitude. It isn't a tenth of a degree difference, and it isn't 20 degrees difference, it's, a degree or two difference. Okay? That's information policymakers need. There is these interesting idea of these zero emission commitment studies, which are sort of a hybrid between the constant concentration and the constant emission scenarios. You could think of them as either being like a constant concentration study, where the concentration is just being held as your current concentration, or you could think of them the other way around. You could think of them as a constant emission scenario, where the amount of emissions the amount of emission is zero. I mean, they're kind of a mix of the two types of studies. But those three terms, constant emission studies, constant concentration studies, and zero emission commitment studies, those are terms you see in literature. Or if you go to a seminar or something like that, they're going to say, I'm comparing these results to the constant emissions studies run by so-and-so. That's what they're talking about, okay? All right. The problem with these zero emission commitment studies, of course, is that they're powered by rainbows and unicorns, right? I mean, how in the world could we get to zero emissions now? How in the world could we get to zero emissions anytime in the near future? Frankly, how can we get to zero emissions anytime in the distant future, since we're so darn good at finding more ways to find fossil fuels? It's all really hard to imagine how any of that could work. They're useful academically in the sense of it helps us understand the magnitude of changes and so on, but in terms of them being realistic, they might as well be powered by unicorns and rainbows. The other term that was on my list there that was we kind of casually keep dropping is stabilization. Climate change stabilization. This idea that if we stopped emitting at some point in the future, or if we at least stopped increasing the amount we are emitting in the future, it seems like there would be some time at which we could stabilize to some new equilibrium temperature and stop, well, actually it's not going to happen if we're still emitting. When we stop emissions, there's going to be some temperature at which we stabilize. And it's not magic, of course. I mean, we're not pulling a new Earth out of a magician's hat here. We're saying there'll be some new temperature that we reach as the Earth, atmosphere, ocean system reaches a new thermal equilibrium in which the total amount of energy in from the sun in the form of shortwave radiation is balanced by the total amount of energy out. The kind of stuff that we spent so much time on in the second module of the course. Well, stabilization then, again, I believe this might be, I think this might be the same figure we showed before, that actually shows, like, for different RCP scenarios here, where we have different radiative pathways, you can see we end up with different temperatures over the course of, like, the rest of this millennium. And you can see how the global mean temperature kind of stabilizes. Now, it only does that if we stop having these emissions here, but that's kind of the information that we get from this idea of stabilization. Again, we kind of touched on this idea before, but effectively this tells us we can pick the future we want. We can decide what stabilization temperature that we want, and then pick the radiative forcing we're willing to tolerate that will get us there. I mean, we're committed to a certain amount of climate change based on what we have already done to the climate system, based on fossil fuels that we have burned and so on. But how much change we get stuck with in the future is in many ways up to us. We can decide based on how much we're willing to cut our emissions. So if we could pick a particular amount of a stabilization temperature we're willing to end up on, we could make a choice about how much carbon. That would tell us what RCP pathway we need to be on, what is the radiative forcing that we cannot choose any more than that. So we can make some choices here. We are on paths that are forking here. We can take the path that says we could pick a stabilization temperature, that is a new equilibrium temperature that we're willing to tolerate, and then figure out the total cumulative amount of greenhouse gases that we can emit between now and then. Or we could pick the peak warming. Remember, a lot of these scenarios, the climate actually hits a peak temperature, and then they kind of stabilize at a slightly lower temperature. We could pick that peak warming that we're willing to tolerate, and then the actual stabilization temperature will be a little bit lower than that, but that peak warming is where the worst of the melting of sea ice is going to happen, and the worst of deglaciation is going to happen, and so on. To some extent, that peak, that highest temperature we reach, is kind of in some ways more important than the stabilization temperature along the way. And in fact, from the point of view of like the science of it, this latter idea turns out to be the more intellectually rigorous one. It's a more general concept than picking the stabilization temperature. It's to pick the highest temperature we're willing to tolerate in the future, recognizing that the stabilization temperature will probably be a fraction of a degree cooler than that. And it turns out that tends to be the one that is more realistic in terms of how we can simulate such things and so on. Okay, so if we're willing to, if we think the idea is we need to pick a temperature, some kind of stabilization target or some kind of peak temperature target or whatever, what should we pick? It's apparently up to us. Well, the most common target that you often hear about is 2 degrees Celsius. That is the motto of like that Paris Climate Accord from 2015. I stole this piece of clip art here from some news channel's website and so on. That is the number that that is the target that you most often hear thrown around. That is to limit global temperature increases to 2 degrees higher than pre-industrial levels. And that's why they picked that at the Paris Climate Accord. You can see the Eiffel Tower there in the background. And 2 degrees compared to pre-industrial is a very ambitious target, considering we know we've already got about 1 degree Celsius of warming, and we know we have some committed warming still to come based on what we've already emitted. There's nothing we can do about that. And so this is a really ambitious goal. It means that we have to make changes really fast. That's, of course, part of the reason why they chose that goal. Now, this climate target of 2 degrees warmer than pre-industrial is not the only target that has been proposed. It's not the only target that was debated at Paris and so on. For example, a more ambitious, probably impossibly ambitious goal would be 1.5 degrees Celsius compared to pre-industrial. We probably can't reach that. Just committed warming will get us over that. We could define targets based on like carbon dioxide concentrations. For example, let's make it our goal to limit carbon dioxide concentrations to 350 parts per million. Well, that ship has sailed. We're already at 400, but you understand the idea. We could pick a value and say, rather than picking a temperature, let's pick a carbon dioxide concentration. Harder to sell the public on things like that. Or we could talk about like limiting the rate at which we are adding carbon dioxide, or limit the rate at which we're willing to accept temperature change. That can actually be an important strategy. Gradual temperature increase could be more suitable for adaptation, not necessarily like critters, that kind of adaptation. I mean like human adaptation. If we could reach a climate change of say 3 degrees Celsius, but we could take longer to get there and have more time to adapt, that might not be, from a policy point of view, such a terrible idea. So certainly many ideas about how to define a climate change target were discussed at meetings like Paris and so on. But it bears so much repeating. You cannot stress enough, regardless of what we pick as our target or how we pick at that target, it's a thing. It's a time in the future. We will reach a time in the future, some point in the future, where we have no choice, but we have to get the greenhouse gas emissions to a big fat 0. No matter what we pick, we have to at some point hit 0 emissions. I don't mean like as in we need to stop increasing our emissions. That would be relatively easy. I mean we need to stop having emissions at all. Because no matter what we pick as a target, if we keep adding, we'll overshoot that target. It doesn't matter if that target is terrible. If that target is 5 degrees Celsius, we don't like to live that on that planet, and we'll blow right through that goal if we don't at some point hit zero emissions. It's a hard policy point, but basically, in order to achieve any target at all, an optimistic target, a pessimistic target, a very green target, a very climate unfriendly target, it doesn't matter. Any target whatsoever requires that it's simply a matter of when we reach zero greenhouse gas emissions, not if. That is very hard for climate change. Now, for example, so where is that? Okay, so for example, I got this chart from the Carbon Dioxide Information Access Center, and it's basically showing here for different amounts of total amount of carbon dioxide emissions, PGCs, petagrams of carbon, that's the same thing as gigatons of carbon. What is the typical, what will the temperature be? And you can see, because there's an ensemble here, there's actually a wide range of different possibilities, with red being the most likely answer here. Alright, if we are willing to tolerate 2 degrees Celsius, that's going to be our target here. We can read across from 2 degrees Celsius, and we see that it's somewhere around 1,000 gigatons of carbon that we can have added to the Earth's atmosphere. And just for the record, according to the the Carbon Dioxide Information Access Center, since the Industrial Revolution, until the year 2000, we emitted about 440 gigatons of carbon to the atmosphere, which is a lot smaller than 1,000. So we have about, as of the year 2000, we had about 600 gigatons of carbon to go before we hit 2 degrees of climate change. But let's see, that's a while ago. And we're emitting carbon dioxide into the Earth's atmosphere at a rate of about 10 gigatons a year. So let's just say by the year 2020, if we haven't done anything yet by then, because there's like a presidential election that year, we'll have had 20 years of adding 10 more gigatons per year. We'll have added 200 more gigatons just in the first 20 years of this century. So that 440 will now be up to 640 gigatons. See how we're crashing forward toward that 1,000 gigatons. All right? We're going to have a hard time stopping burning fossil fuels by 1,000 gigatons. We don't have a lot of time to make these choices. Uh-oh. That's a big problem. Alright, before we go on to part 3 of this lecture and start talking about some other ways in which this is horrible, let's go through a couple quick questions. Question 5. The carbon cycle removes carbon dioxide from the atmosphere. Wait, so why then do we describe global warming due to carbon dioxide emissions as being irreversible? Is it A, even though the carbon cycle removes carbon dioxide from the atmosphere, it doesn't do so until that CO2 has already caused its radiative forcing? B, is it because it takes much longer to remove carbon dioxide from the atmosphere than it does for the carbon dioxide in the atmosphere to cause climate change? Is it C, the type of heat that is added to the atmosphere due to carbon dioxide concentrations is stored as latent heat in water vapor molecules? Or is it D, this is a trick question, climate change due to carbon dioxide is not considered irreversible, only climate change due to aerosols is? Which of those 4 is the right choice there? Make a choice from those 4 options and get a little feedback before you move on to a 6th question.